welcome everyone for today's talk by Ankit Garg. Before we start, let me mention next talk in 2 weeks will be by Eric Blaze on monotonicity testing. And we have a few groups joining today, so Lydia, maybe you want to go around the table quickly.
Thanks, Odette. We have Anush from Texas A&M. Hello. Then we have Dave from Michigan and Apple. We have Piyush and the group from Caltech. Hi. And we have the group from NYU. And back to you, Odette.
Okay, all right. And let me mention that we have a few people helping us here behind the scenes. We have Gautam Kamat, we have Clément Canon, Thomas Vidic, and Anindya De here with me. And let me also mention again that if anyone listening to us wants to recommend future talks, please let us know. There's a form on the website, or just drop us an email. Any ideas are welcome. Today's speaker is Ankit Garg. Ankit Garg is from Princeton University. He's advised by Mark Braverman. This is last year or last month or week.
Last
month. Essentially, he's graduating very soon. His work is in information theory, as quite broad, doing communication complexity. This had some nice work in parallel repetition, even some quantum. And today he'll tell us about something quite different, very interesting results. He won the Siebel Scholarship from the Siebel Foundation and the Simons Award for graduate students. He also won the Best Paper Award in ICS 2013. So today Ankit will tell us about the result related to non-commutative rank. Sounds scary, but I can assure you I've heard this before. It's very nice, lots of connections to beautiful areas in mathematics. So welcome, Ankit.
Thanks, Odette, for the introduction. So can everyone hear me?
Yep.
Yeah, okay. Okay, so thanks everyone for joining in. I'll be talking about operator scaling and its applications to give a polynomial time algorithm for computing non-commutative rank of symbolic matrices. So I've changed the title a bit. On the website it was non-commutative rational identity testing. So computing the rank of non-commutative symbolic matrices, it's a bit more general problem than non-commutative rational identity testing, and I'll be talking mostly about this as an application of operator scaling. And this is joint work with Leonid Gurwitz, Rafael Oliveira, and Avi Victorson. Okay, let's start. So here's a rough outline of the talk. I'll first go over the classical matrix scaling, which many of you might know about. Then I'll define its generalization called operator scaling, which was first studied by Gurwitz. Then I'll move on to, we give a polynomial time algorithm for operator scaling, and which has applications to computing non-commutative rank of symbolic matrices. I'll define what these terms mean. So it turns out this connection is really two-way. So operator scaling helps us give a polynomial time algorithm for non-commutative rank, but also the techniques from non-commutative rank, especially theorems from invariant theory, they help us analyze operator scaling. Okay, and after defining non-commutative rank and setting up the techniques, I'll give you the analysis of the algorithm for operator scaling, and then I'll end up with some conclusion and open problems. Okay. So let's start with matrix scaling. So in the setting of matrix scaling, we have a non-negative n by n matrix A. Its entries are real non-negative numbers. A matrix B is called a scaling of A if there exist R and C, which are positive diagonal matrices, and B equals R times A times C. Okay, so in other words, the entry Bij is equal to Rii Cjj times the entry Aij. Okay, so if if there are such R and C positive diagonal matrices, then B is called a scaling of A. And B is called doubly stochastic if all its row and column sums are 1. Okay. Now, Cohn in 1964 studied the following question: given a non-negative matrix A, find a scaling of it B, which is doubly stochastic. Okay. Find a scaling which is doubly stochastic if 1 exists. He asked the following question. and he proved that if all the entries of A are strictly positive, then a doubly stochastic scaling of A exists. And he also proved that a natural iterative algorithm for it converges. Okay, so Cohn proved this in 1964. So before I go on to describe this natural algorithm, are there any questions about the definitions? Okay. Okay, so to define this natural algorithm, given a matrix A, let's define a diagonal matrix R of A whose ith diagonal entry is the ith row sum of A inverse. Okay, so Rii is just the ith row sum of A to the power -1. Similarly, the matrix C of A, its jth entry is the jth column sum of A to the inverse. Okay, so these are matrices that encode the row and column sums of A. Okay. Now, given these matrices, we define operations called row normalization and column normalization. So in row normalization, what you do is you just normalize all the rows of A to be 1. Okay, this is easy to do. You just, the new matrix A is R of the old matrix times the old matrix. Okay, so when you do this, all the row sums of the new matrix are 1. Okay, column normalization is you normalize all the column sums to be 1. You multiply the old matrix with C of the old matrix. Okay, so these are the operations, row and column normalization. And now the algorithm, the iterative algorithm is really simple. Okay, you normalize the rows. This way you may unnormalize the column. You normalize the columns again. You might destroy the rows, but you do this again. Okay, you keep doing this for n steps. You row normalize, then column normalize, and repeat. Okay, at the end you get some matrix. Let's denote by A hat and just output A hat. Okay, so this is the natural iterative algorithm that Cohn proved that it converges. Okay, so Cohn in 64 proved that as n tends to infinity, the output A hat converges to be doubly stochastic. Okay, so the row and column sums all get closer and closer to be all ones. Okay, and so Cohn gave no explicit bounds on the rate of convergence. Okay, so since Cohn's work, there have been plenty of works on this matrix scaling, proving a variety of theorems. These are some of the references, and it has found applications in statistics, numerical analysis, operations research, combinatorial geometry, approximation of the permanent, and so on. Okay, I'll talk about some of these applications, but it's a really useful problem. Okay, so this is matrix scaling. Moving on to the convergence rate. Okay, so what do we know about the convergence rate of this algorithm? So Franklin and Lawrence in '89, they were the first ones to prove that in fact this algorithm converges in polynomial number of iterations. Okay, so I'll show you analysis due to Lineal, Samrodinsky, and Wigderson in '98. They proved that this algorithm converges in polynomial number of iterations, and in fact their analysis is a bit more general. You don't require all the entries to be strictly positive. It converges under a more general condition. Okay, so to move on to the convergence analysis, I'll need to define a distance of a matrix to doubly stochastic. Okay, and it's really the natural distance. I mean, you can use any kind of distance you want, and the analysis would probably work. So ds of A is a measure how far A is from doubly stochastic. It's summation over I, Ri minus 1 square plus summation over j, Cj minus 1 square, where Ri and Cj are the row and column sums of A. Okay, so you just have all the row sums, measure how much far they are from 1, add them up, and same for the column sums. Okay, this defines a distance of A from doubly stochastic. Maybe this is not a distance, but we just okay. Okay, so now we have this algorithm for n steps. You alternatively do row and column normalization, and the question is, for what value of capital N does the distance is at most epsilon? Okay, this is the question. And Lineal, Samrodinsky, and Wigderson proved that if the bit complexity of entries of A is, let's say, B, then a polynomial number of iterations in n, b, and 1 over epsilon suffice. Okay, to get this value doubly stochastic to be at most epsilon. Yes.
Yeah, I have a question. Probably this is really stupid, but so it's because the fact that I can make epsilon arbitrarily small, does it mean that actually I can make epsilon zero after sufficiently, like, I mean,
Right, right. Yes, that's a very good question. So the question uh, are there examples where you can get arbitrarily close to doubly stochastic and not actually achieve doubly stochastic? And in fact, there are such examples. I mean, for example, you can think of a matrix, 2 by 2 matrix, whose 3 entries are 1 and 1 entry is 0. Okay, and you can prove that you cannot achieve doubly stochastic, but you get arbitrarily close to doubly stochastic. Okay, yes, thanks. Okay, yeah, so so LSW proved that polynomial number of iterations suffice, and I'll show you how their analysis worked. Okay, okay. Any other questions? Okay, okay. So I mean, for these algorithms, we need a potential function to measure how much progress we are making, and the potential function they used was the permanent of the matrix A. Okay, so permanent polynomial is defined as just similar to the determinant, just that there are no signs. So note that we can, without loss of generality, assume that A is row normalized. Okay, I mean, it's really easy to make the row sums 1. So initially, the permanent of the matrix A is at least 2 to the minus bn, where b is the bit size of the entries. Okay, this is easy. Permanent of A is at least the product of the diagonal entries. Each of the diagonal entries is at least 2 to the minus b, so permanent is at least 2 to the minus bn. Okay. So as long as the matrix is far from being doubly stochastic, let's say epsilon far from being doubly stochastic, the normalization step increases permanent of A by a factor of 2 to the epsilon. Okay. So this again can be proven by some sort of AMGM inequality. I won't go into the details, but as long as you're far from doubly stochastic, permanent of A always increases. And permanent of A is at most 1. If A is row or column normalized, permanent of A is at most 1. This is also easy to prove via, let's say, actually this is really elementary. Okay, so we have these 3 conditions, and now these obviously imply that we should achieve that doubly stochastic of A is at most epsilon in Bn over epsilon steps. Okay. So permanent has a lower bound, it keeps increasing as long as you're far from doubly stochastic. It has an upper bound, so you must reach close to doubly stochastic in Bn over epsilon steps. Okay.
Ankit?
Yes.
Where do you use the fact that A is positive? Assume the permanent, I guarantee you that the initial permanent is like at least 2 to the minus bn. Is that enough? Or?
Yes, very good question. So the question is, does this algorithm converge only if A has all strictly positive entries, or let's say if you have a lower bound on the permanent? Yeah, it converges if there's a lower bound on the permanent. You don't need all the entries to be strictly positive. Okay, so you only need permanent to be positive.
Maybe it's worth pointing out that the normalization operation, say row normalization, has a very clear effect on the permanent, right?
Yes, yes.
If you multiply the first row by 2, the permanent goes up by 2, right?
Yes. So if you multiply A by a diagonal matrix, permanent changes by the determinant of the diagonal matrix. Yes, exactly. Thanks.
Actually, I have a question then. So so initially, if there's a lower bound on the permanent, so the initial potential function is something.
Yes.
But the step that every time you do this normalization, the potential function must increase by 2 to the epsilon. What does that like? Does that use like non-negativity of the entries?
No, that doesn't use non-negativity of the matrix. So as Oded pointed out, when you do the normalization, permanent of A increases by, let's say you multiply A by a diagonal matrix R, permanent of A increases by the determinant of R. Okay. Okay. And as long as you're far from doubly stochastic, it can be proved that determinant of R has a lower bound of 2 to the epsilon.
I see. And okay, good. Okay.
Okay. Yeah, so this is the analysis, and as Oded pointed out, there exists an almost doubly stochastic scaling of A only if permanent of A is greater than 0. You don't need all the entries to be strictly positive. Okay, and in fact, okay, so this gives us the first application, an alternate algorithm for determining if a bipartite graph is perfect matching. Okay, so LSW also proved that if there is a doubly stochastic scaling of A, where you get, let's say, 1 over n close to being doubly stochastic, then permanent of A has to be at least 0, has to be greater than 0, strictly positive. Okay, if there exists a doubly stochastic scaling of A, then permanent of A is greater than 0. Okay, So by running this scaling algorithm, you can check whether permanent of A is greater than 0 or not, which is actually just checking whether a bipartite graph with the adjacency matrix A has perfect matching or not. Okay, so this gives a very different algorithm for checking if a bipartite graph has a perfect matching. You start with the adjacency matrix A of the graph, and you do scaling. If you get close to doubly stochastic, then output it has a perfect matching, otherwise not. Okay, but it's slower algorithm, but it's a very different algorithm for perfect matching. Okay. Okay. Any questions? Okay, the second application that LSW give is for approximating the permanent. Okay, so given a non-negative matrix A, we want to approximate the permanent of A. So what do you do? Find a doubly stochastic scaling B equals RAC of A, and output determinant of R inverse times determinant of C inverse. Okay, and I claim that this is a good approximation of the permanent of A. Okay, why is that? As Ored pointed out, permanent of A is exactly equal to determinant of R inverse times determinant of C inverse times the permanent of B. Okay, it's only true if R and C are diagonal matrices, which they are in the scaling algorithm. Okay, now since B is doubly stochastic, permanent of B is at most 1 and is at least e to the minus n. Okay, this follows from the van der Waals conjecture, which is now a theorem, right? So this algorithm provides you a e to the n approximation to the permanent of A. Okay. So note that it's a deterministic algorithm. Now we have better 1 plus epsilon randomized algorithms, but still one of the best deterministic algorithms for approximating permanent. I think recently they have been square root 2 to the n approximations by I think breakthrough of Gurwitz and Samrudinsky, but this still is very cute application of the scaling. Okay. Okay. Any questions? Okay. So this was about matrix scaling. Oh, sorry. Okay. I should also mention that Gurwitz and Yanios they provided an alternate analysis of Synchron's algorithm using the notion of capacity. Okay. So a capacity of a matrix A is defined as how much it shrinks the product of the entries of the vector it acts on. Okay. So it's infimum of the product of AX I such that the product of xi is 1 and x is a non-negative, x is a positive vector. Okay, and so I mean this notion of capacity will be very useful for us in the operator case. This is actually what we generalize potential function will use. Okay, and Synchron's algorithm can be seen as an alternating minimization algorithm for a convex formulation of capacity. So as written, capacity of A is a non-convex program, but it can be written as a minimization of relative entropy, which is a convex program, and Synchron's algorithm is just a alternating minimization algorithm for that convex program. Okay, so this is just a side note. Okay, so this was matrix scaling. Now I'll move on to its generalization, operator scaling, which is really the main part of the talk. Okay. Okay, so before that, are there any questions about matrix scaling? Okay, so Gurwitz in 2004 he generalized the matrix scaling to quantum operators. Okay, so what does that mean? So non-negative matrix A is just a map from Rn to Rn. Okay, and since it's non-negative, it maps non-negative vectors to non-negative vectors, right? So generally, when you generalize to the quantum setting or the non-commutative setting, vectors become matrices, and non-negative vectors would mean PSD matrices, right? So our objects of study in the quantum case or the non-commutative case would be operators from n by n matrices to n by n matrices, which will map preserve PSDness, which will map PSD matrices to PSD matrices. Okay, so we're interested in operators from n by n matrices to n by n matrices which preserve PSDness. Okay. And in fact, we'll study a special class of these operators called completely positive operators. Okay, so I won't go into the definition of completely positive, but an alternate characterization is that such operators look like this. There are M matrices A1 to AM, and the action of T on X is defined as summation AI X AI transpose. Okay, such an operator is called completely positive. And so these arise, completely positive operators arise naturally in quantum mechanics. These are the ones actually that can be implemented in the real world. Okay. Uh, and okay, so any questions about the definition of completely positive operators? Okay. So given a completely positive operator T, this is a very natural notion of the dual of it, T star, which is defined as summation AI transpose X AI. Okay, you just switch the role of AI transpose as an AI. So this will be called the dual of T star. So now I'll define what it means to be doubly stochastic in this setting. Okay. So an operator T is called doubly stochastic. It's also sometimes called unital in the quantum papers if T maps identity to identity and the dual of T also maps identity to identity. Okay, then T will be called doubly stochastic. In terms of the matrices A1 to AM, what this means is that summation AI transpose should be identity and summation AI transpose AI should be identity. Okay. If these two conditions are satisfied, then T is called doubly stochastic. Okay, or this collection of matrices A1 to AM is called doubly stochastic. Okay. And what does scaling mean in this setting? So given a completely positive operator T, T tilde is a scaling of T if there exists invertible matrices B and C such that the action of T tilde on X is exactly B times T CX C transpose times B transpose. Okay.
Ankit?
Yes.
So AIs are PSD matrices or they're matrices with whose entries are positive?
So AIs are arbitrary n by n matrices.
Okay.
Yes. AIs are arbitrary n by n real matrices. Okay. So T tilde is a scaling of T if there exists arbitrary invertible matrices B and C such that T tilde of X is B T C X C transpose B transpose. Okay, it's easier to see the action on A1 to AM. Okay, so the new A tilde i's we get for this operator T tilde is AI tilde is B AI C. Okay, so you multiply on the left and the right by invertible matrices. Okay, so that's what this scaling is doing. Okay, so all the A1 to AM you multiply on the left and the right by the same invertible matrices B and C. Okay, so this is scaling. And Gurwitz in 2004 studied the following question: given a completely positive operator T, find a doubly stochastic scaling of it. Okay, if one exists. So right now it might seem like a exotic question, but as we'll see later, it has connections to deep questions in mathematics and TCS. Okay. Okay, so this is the operator scaling question. And again, Gurwitz suggested a natural iterative procedure for finding a scaling and proved that it converges. Okay, under some non-degeneracy conditions. He also proved that it converges in polynomial number of iterations in some special cases. Okay. So the condition of convergence will be actually connected to non-commutative rank of symbolic matrices. Okay, so which will come later. So hold on for the condition of convergence. But I'll present the algorithm now. Okay, for operator scaling. Okay, so we're given this matrices A1 to AM. Again, I'll define some normalizing matrices connected to this A1 to AM. So the left normalizing factor is summation AI transpose, the negative square root of that. Okay. The right normalizing factor is the negative square root of summation AI transpose AI. Okay. So these are two normalizing matrices. And now, given these two normalizing matrices, we define two operations. The first one is called left normalization, where we multiply the AIs on the left by the L matrix. Okay. So note that once we do this, this ensures that summation AI tilde transpose identity. Okay, so we just normalizing it. Okay, and again similarly the right normalization we multiply on the right by the R matrix, which ensures the opposite condition: summation AI tilde transpose AI tilde is identity. Okay, so these are two normalizations which ensure one of the two conditions that we wanted to satisfy. And now, the algorithm is obvious, right? For n steps, we left normalize, right normalize, we keep doing this and output the operator at the end. Okay. So this is the algorithm for operator scaling. And Gurwitz in his paper proved that as n tends to infinity, the output converges to being doubly stochastic. Okay. He also gave polynomial convergence bounds in important special cases. For example, when all the AIs are rank 1, he proved that this algorithm converges in polynomial number of iterations. So this had some nice implications. For example, it gave alternate algorithms for matroid intersection problems, also some special cases of Edmonds problems, but we'll come to it later. Okay. So right now, this is our scaling algorithm, and what we want to prove is that this converges always in polynomial time. Okay. Okay. So to present the analysis of the convergence rate, again, I'll define some distance to be doubly stochastic. I mean, you can choose any distance. We'll choose this trace of ti minus identity square plus trace of t star I minus identity square. Okay. If t is exactly doubly stochastic, this distance is 0. And we have this algorithm, and the question is for what value of capital N does this doubly stochastic measure is at most epsilon. Okay, so the main theorem we prove in our paper is that if the bit complexity of the entries of the matrices A1 to AM is B, then polynomial number of iterations suffice to drive this doubly stochastic measure to epsilon. Okay, so it's polynomial in N, bit complexity, and 1 over epsilon. Okay, so in these number of iterations, you converge to epsilon doubly stochastic. Okay, so any questions to this point? Okay. Okay, so to present the analysis, we need a potential function. So it turns out, I mean, you might hope that there's some quantum generalization of the permanent which works in this setting, and in fact there is one, and Gurwitz defined it in this in his paper. He called it the quantum permanent. I won't define it here, but the problem is it doesn't always give you convergence. I mean, that potential function works in some special cases but doesn't always work. That's why Gurwitz wasn't able to prove that the algorithm always converges. So in what turns out is that the notion of capacity I told you in the classical setting, if you generalize it to the quantum setting, that is the right potential function to look at. Okay. In fact, I mean, it's nothing new. Gurwitz already mentioned this potential function in his paper. Okay. So capacity of an operator T is defined as how much it shrinks the determinant of matrices. Okay, so it's infimum of determinant of T of X, such that determinant of X is 1 and X is strictly positive definite. Okay, so this is the notion of capacity. So I can't give you much of intuition why this is the natural potential function, but I'll tell you that this notion of capacity has a rich history. So this appears a lot of times in Gurwitz's papers. For example, in his proof of van der Waals conjecture, in his study of approximating mixed discriminants, and in his studies about hyperbolic polynomials, like various avatars of this capacity appear in his papers all the time. And even here, this notion of capacity is the right one to look at as a potential function. So just as a side note, this shouldn't be confused with the capacity of operator T when it's viewed as a quantum channel. Okay, it has nothing to do with that capacity, like the information theoretic capacity. I don't know why he calls it capacity, but it's just how much the operator T shrinks the determinant. Okay, so as before, we'll assume that T is right normalized. It's easy to do. So initially, capacity will be at least some 2 to the minus poly NB. Okay, as long as capacity is greater than 0 to start with. Okay, this will be true. This is actually the main theorem of the paper, which I'll prove later. So initially, the capacity will be at least exponential minus poly n. As long as it's far from epsilon, doubly stochastic, normalization increases the capacity by a factor of 2 to the epsilon. Okay, the second point is actually very analogous to the point in matrix scaling, and it's easy to prove by AMGM inequality. And capacity is always bounded by 1. This again can be proved by AMGM inequality. So really the main step is point number 1. Okay, but given these 3 conditions, it's easy to see that you achieve doubly stochastic T at most epsilon in poly n by epsilon steps. Okay, because you start with a potential function which is at least to the minus poly n, it increases at every step and it's bounded by 1. So this process should stop somewhere. Okay. And the main contribution of this work is proving that this capacity is at least to the minus poly nb, okay, whenever the algorithm converges. Okay.
Ankit?
Yes.
Quick question: does this include the standard, the classical case, the special case?
This includes this classical case as a special case. So I mentioned that Gurwitz and Yanlios, they proved an analysis of the matrix scaling using the notion of capacity of the matrix. So this analysis is a generalization of that analysis.
There's a way to take an instance of an arbitrary matrix and convert it into this sequence of AIs such that the scaling question for the AIs is equivalent to the original question. Okay.
Yes.
Thanks.
And in fact, given A, the matrices A1 to AM would be, you would get n square matrices where you zero out all the entries except the ijth entry. For all
square root, maybe you want square root on that entry, right?
Yeah, maybe the square root on the entry. Yes.
Yeah, I see. Yeah. Okay, thanks.
Okay. Okay, so this is the analysis of the algorithm. So the main contribution is proving this lower bound on the capacity. And to prove this lower bound, we'll need to borrow techniques from non-commutative rank and invariant theory. And also our main application for operator scaling is non-commutative rank. Okay. So next I'll move on to the notion of non-commutative rank of symbolic matrices. Okay. So, and after that I'll give you the complete analysis of this algorithm. Okay, mainly the lower bound capacity. Okay, any questions about operator scaling? Okay. Okay, so I'll move on to non-commutative rank of symbolic matrices. Okay, what is this notion? Okay, symbolic matrices. So we look at matrices of the form summation xi ai. So A1 to AM will be n by n matrices over some field F, and the x1 to xm will be formal variables. Okay, so they might be commuting, or in our setting they will be non-commuting. Okay, and the matrix L has entries which are linear polynomials in x1 to xm. Okay, an alternative way to view L is that its entries are linear polynomials in this formal variable. Okay. And the central question about the symbolic matrices is compute the rank of this matrix L. Okay, so what does that mean? So this question has a dual life depending on whether the variables are commuting or non-commuting. Okay, and when the variables are commuting, it's a central question in TCS to compute the rank of the cells. Okay, so I'll first go over the setting of commuting variables x1 to xm. Okay. So we have this symbolic matrix whose entries are linear polynomials in x1 to xm. So the question is compute the rank of this L, and the rank of this L I'll measure over the field of rational functions in x1 to xm. Okay. So we can have we have that field of rational functions whose elements are ratio of two polynomials in x1 to xm, and I want to compute the rank of L over that field. Okay, and this is the famous Edmonds problem. I'll assume usually F is large enough. Okay, so alternative way of viewing this rank is that it's the maximum rank of a matrix in the subspace spanned by A1 to AM. Okay, so the maximum rank of summation alpha AI, where alpha 1 to alpha m are elements from the field F. Okay, so you want to compute this maximum rank in the subspace, and there's a very natural randomized algorithm for this problem. You just plug in random values from x1 to xm, okay, from the underlying field, and compute the rank of that matrix. So this was, I mean, it follows easily from Schwarzschild lemma that when you plug in random values from x1 to xm and compute the rank, what you will achieve is the maximum rank. Okay, so there's a efficient randomized algorithm for this problem. So there's an efficient randomized algorithm and an efficient deterministic algorithm. It's a major open problem in TCS. So it captures the polynomial identity testing problem or PIT. So this was shown by Valiant in 1979, where he showed how to encode arithmetic formulas as determinants of symbolic matrices. Okay. And thus computing, actually checking the rank, whether the rank of the symbolic matrix is full or not, captures the famous polynomial identity testing problem. An efficient deterministic algorithm for this problem also implies certain form of circuit lower bounds, as was shown by Cabinets and Impagliazzo in 2004. Okay, so this Edmonds problem is a really important and fundamental problem in TCS. Okay, it's de-randomization. Okay. So this is the case of commuting variables, and now I'll move on to non-commuting variables. Okay, and what life does this problem take when the variables are non-commuting? Okay, so any questions about the commuting case? Okay, so non-commuting variables. So again, we have the symbolic matrix L, and the variables x1 to xm are non-commuting. So what I want to do is compute the non-commutative rank of L, and I mean the rank of L will be taken over the field of non-commutative rational functions. Okay, so what the hell is this object, right, denoted by this? So it turns out it's extremely hard to define, or extremely tricky to define, at least this field of non-commutative rational functions. So in the commutative case, every rational expression in x1 to xm can be written as a ratio of two polynomials. But in the non-commutative case, not every rational expression in these variables can be written as a ratio of two polynomials because of non-commutativity. In fact, you could have expressions where you have nested unbounded number of nested inversions. So that's, for that reason, it's really hard to define this what is this Q field or field of non-commutative rational functions. So I won't define you this quantity in this talk. So just point out that constructions for this were given by people in non-commutative algebra. There's a typo. It should be Amit Sur. So there are famous people, Amit Sur and Cohn, who gave the constructions of this field. For the purpose of this talk, you can think of non-commutative rank as the following quantity. Okay. So we look at the maximum rank in the span of A1 to AM, but now coefficients will be matrices. Okay. So you pick a dimension D, and you pick matrices T1 to Tm, which are D by D matrices, and look at summation Ti tensor Ai. You compute the rank of that quantity and normalize it by D. Okay. So supremum over D, the rank of summation Ti tensor Ai divided by D, where T1 to Tm are arbitrary D by D matrices. This supremum is actually equal to the non-commutative rank of L. Okay, or to the definition above, which I didn't define. Okay, so this is the definition you should keep in mind while studying non-commutative rank. So I guess, so one point to make is that from this definition, it's not clear if this thing is an integer, right? And it's also not clear if this supremum is achieved. But in fact, this non-commutative rank is an integer, and the supremum is achieved for some finite dimension D. Okay. Okay. So any questions about this definition? Actually, this is really a theorem, but I'll defining this way in this talk.
So is it possible to give like an explicit bound on what the D must be, like that you can always achieve it for like n D equals 2 to the 2 to the n or
yes.
something like this?
That's a very good question, and in fact, such a bound, you can place an exponential bound. So the before our paper there was a bound, and in fact that bound will be crucial to the analysis of capacity. So before our paper, the best bound was exponential. Now it's polynomial, but the exponential bound is actually what will give us the lower bound capacity. Okay, so I'll come to that. It's a very good question.
Sorry, so do you use the exponential bound to actually get a polynomial bound?
We use the exponential bound to get a polynomial time algorithm. Right?
Okay.
The algorithm is still the scaling algorithm.
Okay.
Yes.
The polynomial bound is separate. It's a more recent result.
Yeah, polynomial bound is separate. It's a more recent. Yeah, I'll come to this this question. It's a very fundamental question. What is the D bounds on D you can achieve? Okay.
That's good.
Yeah, thank you. Okay. Okay, so one thing is that you might ask whether does it make a difference if you tensor with matrices or if you just take linear combinations of AI, does the rank change? In fact, these notions of commutative rank and non-commutative rank can differ. So one of the most famous example is this skew symmetric matrix in 3 variables. So you look at this matrix L, it has variable x, y, z, and it is skew symmetric. So when x, y, z commute, this matrix is singular because it is skew symmetric and hence its determinant is 0. Okay. But when x, y, z are non-commuting, in fact, you can prove that L is not singular. You can plug in some 2 by 2 matrices for these variables x, y, z, which makes the huge 6 by 6 matrix non-singular. Okay, so commutative rank is 2 and non-commutative rank is 3. Yes.
Sorry, Ankit, just to make sure, you're using singular here, but that's equivalent. That's by definition full rank. I mean, rank being full, right?
By singular, I mean not full rank.
Yeah, but that's so I can take a definition before singular means rank is strictly less than n.
So, sorry, yeah, that's what I mean by singular. Yes, rank is strictly less than n. Yeah, thank you. Okay, so this was just to say that these notions can actually differ, commutative and non-commutative rank. Okay, so what is known about this question of computing the non-commutative rank? So it's not even clear if it's decidable. I mean, by decidable, I mean when studying the problem whether non-commutative rank is full or not. Okay, it's not even clear it's decidable. It's taking a supremum over arbitrary dimensions d. So it was shown by Cohn already in 1973, and also in later papers of Cohn and Rothenauer, that this problem is actually decidable. They gave an exponential time algorithm for this problem by reducing it to solving a system of polynomial equations. But the previous algorithms for this problem were all exponential time, even if you allow randomness in the algorithm. Okay. So the main, so what we prove using operator scaling is that when the field, underlying field is the field of rational numbers, then there's a deterministic polynomial time algorithm for computing the non-commutative rank of symbolic matrices. So that's one of the main applications of operator scaling. Okay. Okay. So curiously enough, after like a month of our posting a paper, Ivanios, Shao, and Subramaniam, they gave a deterministic polynomial time algorithm which works over all finite fields and also works over all rational numbers. But their algorithm is actually completely different. Their algorithm uses Wong sequences, which is an algebraic generalization of augmenting paths. Okay, so if you remember, in the perfect matching case, there are two algorithms. There's using augmenting paths, and then there's using scaling. So we generalize the scaling algorithm, and they generalize the augmenting paths algorithm. Okay, so it's really cute. Okay, so this is for non-commutative rank. So you might wonder, like, this is a very exotic problem. What are the applications? So it turns out this has connections and applications to a large number of mathematical areas, and this problem has been studied independently by a huge number of people. So as you already saw, this has connections to Edmonds' problem, which is for when the variables are commuting. In fact, even the non-commutative rank problem captures a sort of identity testing for non-commutative formulas with division. Okay, that's called non-commutative rational identity testing. I won't go into the details. So it is a fundamental problem in non-commutative algebra. So notice that I told you there's this field of non-commutative rational functions which people have constructions of but have no idea what it looks like. So the constructions go by giving equivalence classes of representations of this rational functions, and actually this algorithm gives a polynomial time algorithm to solve the word problem for this field. Okay, given two representations, when do they represent the same element? This was I mean, this problem has been studied by Cohn and others in non-commutative algebra for a long time. So it again has connections to invariant theory. This algorithm solves a fundamental problem in invariant theory and algebraic geometry, determining if the tuple is in the null cone of the left-right action. So and it also arises naturally in quantum information theory, testing if a completely positive operator is rank decreasing. So I'm sorry I won't have time to go define all these problems, but I'll be happy to talk after the talk. Okay, about it. Okay, so moving on to a non-commutative rank and what's the connection to operator scaling. So Cohn proved this really amazing theorem in 71. He proved that the non-commutative rank of a symbolic matrix L is smaller than n if and only if the matrices A1 to AM admit a shrunk subspace. So what do I mean by that? What is a shrunk subspace? A subspace V of F to the n is shrunk by all of A1 to AM if there exists another subspace W whose dimension is smaller and each AI maps V into W. Okay, so pictorially there's a subspace V of F to the n, whose dimension is larger than dimension of V, and each AI simultaneously maps V into W. Okay, so A1 to AM simultaneously shrink a subspace of F to the N. Okay, so that's called a shrunk subspace. And Cohn proved that non-commutative rank is smaller than N if and only if there's a shrunk subspace. Okay, so one direction is, as usual, trivial. If A1 to AM admit a shrunk subspace, it's easy to prove that non-commutative rank is smaller than N. But the amazing part is this is if and only if. Okay, so this is really a analog of Hall's theorem for bipartite matching, right? So what Hall's theorem says is that a bipartite graph has no perfect matching if and only if there is a shrunk subset of vertices. What I mean, for example, look at this 3x3 bipartite graph. Two of the vertices on the left side are mapped into a single vertex. Okay, that's mean they are shrunk into a smaller size subset, and clearly this means that this graph cannot have any perfect matching, right? You cannot match these two vertices to two different vertices on the right hand side. And Hall's theorem, Cohn's theorem is just a linear algebraic generalization of Hall's theorem. So the non-commutative rank is smaller if and only if there's a now a subset is replaced by subspace V on the left hand side such that all the A1 to AM map it into some smaller subspace W. Okay. So this is so this was proven by Cohn in 71. So any questions about this theorem? Okay. So this will what will give us a connection to operator scaling. Okay. So note that in operator scaling we're given matrices A1 to AM and this operator T, and we want to know whether when the operator scaling algorithm converges. So Gurwitz proved in his paper that the algorithm converges if and only if A1 to AM have, sorry, there's a typo. So this should be the algorithm converges if and only if A1 to AM admit no shrunk subspace. Okay, if and only if there is no shrunk subspace, the algorithm converges. I apologize for the error. Okay. And by testing convergence of Gurwitz algorithm, we can test if A1 to AM admit a shrunk subspace or not. Okay, so Gurwitz algorithm converges if and only if the non-commutative rank is full, or A1 to AM admit no shrunk subspace. And we prove that Gurwitz algorithm converges polynomial number of iterations. Okay, so this is the connection to operator scaling. Operator scaling gives you a way to test whether the non-commutative rank is full or not. Okay. Okay. Any questions? Okay. Okay, so now if there are no questions, I'll move on to the analysis of the algorithm, specifically giving the lower bound on the capacity and how non-commutative rank or some bounds for invariant theory play a crucial role in that. Okay, so just a recap for operator scaling. We're given a completely positive operator T in terms of its cross operators A1 to AM. And we also have this symbolic matrix L, which is summation xi to summation xi. So the operator scaling algorithm was for n steps you do left and right normalizations alternatively, and you output the operator you get at the end. And we had this potential function called the capacity of the operator. We had these three steps where we wanted to prove a substantial lower bound on the capacity to start with, and it was easy to prove that capacity always increases by normalization and capacity is bounded by 1. And this will give you the convergence rate of the algorithm. Okay, so the main bound here is the capacity of T should be at least 2 to the minus poly NB whenever the non-commutative rank of L is N. Okay, so whenever the algorithm converges, the capacity should have a substantial lower bound. And how do we prove this lower bound? So before that, as I mentioned, we need this bounds on the fullness dimension of this symbolic matrices L. Okay, so recall that the non-commutative rank of L is N if and only if there exists matrices T1 to Tm of some dimension D such that summation Ti tensor Ai is invertible. And Anindya asked this very important question: what is the value of D that suffices for this connection? Okay, what is the bound on D? So Dirksen in 2001 and Ivanios, Shao, and Subramaniam in their previous paper, they proved that D equals 2 to the poly n suffices. Okay. So you only need to go up to exponential size matrices to check whether the rank is full or not. Okay. So note that this doesn't give a polynomial time algorithm for checking whether non-commutative rank is full or not. You can't really plug in exponential size matrices. But this exponential bound helps in our analysis of capacity and gives a different polynomial time algorithm, namely operator scaling. Okay. So moving on to the lower bound for capacity. So there are three steps in the analysis of capacity. The first step is proving a substantial bound if one of the matrices A1 to AM is non-singular, if it's full rank. Okay, this is really easy to prove. For example, can be proven by I mean, basically you're summing a bunch of PSD matrices and their determinant is at least the determinant of one of them. Okay, so believe me, this is easy to prove. The capacity of T is at least exponential if one of the matrices A1 to AM is non-singular. Okay, the next step is tensoring T with some operator T prime. Okay, so step 2 is there exists some operator T prime acting on some exponential dimension such that the capacity of tensoring of T and T prime is at least some 2 to the minus nd. Okay, so this is achieved by using the fullness dimension bound. Okay, this T prime will really be the operator defined by the matrices T1 to Tm. Okay, so note that there existed T1 to Tm, there exists T1 to Tm such that the summation Ti tensor Ai is invertible. Okay, then you'll choose this operator T prime to be the operator defined by those T1 to Tm, and the condition in step will be satisfied. Okay, so this way you can get a bound on the capacity of T tensor T prime. Okay.
Ankit, so what are you trying to prove? You're trying to prove that capacity of T at the very beginning has some lower bound, right?
Yes, I'm trying to prove that capacity of T is at least 2 to the minus poly n if the non-commutative rank of the symbolic matrix is full.
Okay, and initially you said that if any of the AIs is non-singular, we know how to prove that. That's easy.
Yes, if any of the AIs is non-singular, it's easy.
Okay, so now you're in the case that if all the AIs are singular, then what happens?
Yes, then what happens?
Oh, okay, good. Thanks.
So then what happens is the non-commutative rank is still full. So there exists some matrices of exponential dimension so that when you tensor, then the matrix in that space is invertible. Okay. So when you translate this to the operator setting, what it means is that there exists some operator T prime of acting on exponential dimension so that we have a lower bound on the capacity of T tensor T prime. Okay. This is what it means. And the step 3 is just relating the capacity of T to capacity of this T tensor T prime. And it's again a really simple lemma. Capacity of T is at least capacity of T tensor T prime to the power 1 over D, where D is the dimension of this operator T prime. Okay. And notice that we have a bound of 2 to the minus nd log nd for capacity T tensor T prime, and this 1 over D cancels with the D. So what you're left with is only 2 to the minus n times log nd. And since D is exponential, this is 2 to the minus poly n. Okay. So really the deep, I mean, these are simple calculations. The one of the non-trivial fact you're using is that there exist matrices of exponential dimension that make your matrix invertible. Okay.
Sorry, Ankit, can you explain again how you got to step 2 from step 1?
Okay, so I sort of was trying to skip a step. So in fact, step 1 also holds if not only A1 to AM are invertible, one of them, but there's a matrix in the span which is invertible. Okay, and now we have that a matrix not in the span of A1 to M, but in the matrix span of A1 to AM is invertible, right? So if non-commutative rank is full, then this matrix is T1 to Tm such that this sum is invertible, right? So what that means is that when you define this T prime, sorry, where's my cursor? When you define this T prime to be the operator defined by this T1 to Tm, then for the operator T tensor T prime, there exists a matrix in the span which is invertible, and then you can apply step 1 to it.
And the tensoring operations are kind of one AI at a time.
Sorry, I mean in the tensoring operation, you take the tensors of all the pairs. Basically,
so it's AI with TI.
AI with TJ, AI with TJ for all pairs.
Oh, or pairs. Oh,
yes. Yeah.
Really? Okay. If you go back to the previous slide, that's what you need?
No. We only have the matching here. But basically, if you have all the TI tensor, so all the TJ tensor AI, you can still have a collection of them whose sum is invertible, and that
Okay,
suffices.
I see. So it's bigger than what I thought, but it's saying it still satisfies your step 3 or this capacity.
Well, it's I mean, in the step 1, I said if one of the matrices is non-singular, but actually also holds if sum of a bunch of them is non-singular. Still, you can lower bound the capacity.
Okay, thanks.
Okay. Okay, so note that in step 3 we needed the capacity of T that has a lower bound in terms of capacity T tensor T prime. In fact, this notion of capacity is multiplicative. Okay, so capacity of T tensor T prime appropriately normalized is equal to the product of capacities of T and T prime. We only needed the easy direction analysis, but it's very curious that the hard direction in fact holds. The capacity uh, is multiplicative. So what this really means is that when you're doing this optimization for T tensor T prime, the optimizing matrix whose determinant is trunk is also a tensor product over the spaces. Okay? And the hard direction in fact is proven by operator scaling. Okay? Okay, so this was the analysis of capacity. So moving on to the fullness dimension, I mentioned that after our work, actually within like 10 or 15 days, Dux and Makam, they proved that a bound of n-1 on the dimension of matrices suffices to witness full rank. Okay, and they use ideas from the previous paper of Ivanios, Shao, and Subramani. So this linear bound actually doesn't affect analysis much. I mean, on the capacity, instead of 2 to the minus poly n, you will get something like 2 to the minus n. And it improves the running time a bit, but doesn't affect it much. But this bound immediately implies a randomized polynomial time algorithm for non-commutative rank. You just plug in random matrices of dimension n-1 and check whether you've witnessed full rank or not. Okay. So and in fact this algorithm works over all fields. Ivanios, Shao, and Subramaniam in their follow paper, they use this bound among other things such as Wong sequences to give a deterministic polynomial time for algorithm for non-commutative rank over all finite fields and also over rational numbers. Okay.
So is your algorithm working only for rational, like?
Yes, our algorithm only works for rational numbers. Yeah, because we need these notions of PSD and operators and so on. Okay, so this is the first application of operator scaling, computing the non-commutative rank. The second application is computing the capacity. Okay, and I should really thank Audit for this. This came out in discussions with him. So there's a polynomial time algorithm to compute 1 plus epsilon approximations to the capacity function. Okay, and the algorithm is really this, analogous to the computing the permanent. So given an operator T, you find a doubly stochastic scaling T tilde of T. Let's say T tilde is given by invertible matrices B and C. You output determinant B to the power minus 2 times determinant C to the power minus 2. Okay, so what it turns out, you can check this. It's a simple calculation that capacity of T is exactly this product of determinants times the capacity of T tilde. And since T tilde is doubly stochastic, it can be proved that capacity of T tilde at exactly 1. Okay, so this gives you an exact algorithm for computing the capacity of an operator T. So this is in the exact case, but the same analysis also works in the approximate case. Okay, so you might ask, what do you want to compute capacity? So it's a very interesting point. So capacity of T is given by this program, minimizing the determinant of T of X, as the determinant of X is 1. As written, it's a non-convex program, and we don't know how to write it as a convex program. The Gurewitz algorithm, it actually is an alternating minimization algorithm for capacity. It can be interpreted in this way. And so this provides another concrete setting in which alternating minimization provably works for solving a non-convex program. And in an upcoming paper with the same set of authors, we give an application of this polynomial time algorithm for capacity to computing best constants in Branscombe-Lieb inequalities. Okay, so this is about computing capacity. Any questions?
Ankit?
Yes.
Yeah, if you go to the previous slide, Just to make sure, so how come suddenly you have log 1 over epsilon? Previously, during the holdover, with 1 over epsilon there.
That's a very good question. The analysis that we present in the paper, that would only give 1 over epsilon instead of log 1 over epsilon. But actually the analysis can be improved, and you can prove that when you get closer and closer to being doubly stochastic, the rate of convergence actually is exponential.
Thanks.
Yeah. Okay. 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 So if there are no questions, I'll move on to the conclusion and some open problems. Okay. Okay. So we give a polynomial time convergence for operator scaling. This was used to get the first deterministic polynomial time algorithms for computing non-commutative rank of symbolic matrices. And also using this, we get a polynomial time algorithm for computing capacity, which is actually a non-convex program. Okay. So there's a very interesting application to the Edmonds problem. So notice that the Edmonds problem was computing the commutative rank of this symbolic matrix L. Okay. And what Fortin and Rothenauer proved in 2004 is that the commutative rank of L is at most the non-commutative rank, which is at most twice the commutative rank. Okay, so non-commutative rank provides a two-factor approximation to commutative rank, and our algorithm implies that there's a deterministic polynomial time algorithm for a two-factor approximation for commutative rank. Okay, so this opens up a really nice challenge for de-randomization. Can we achieve a 1 plus epsilon approximation for commutative rank in deterministic polynomial time? Okay, so this provides slightly different direction for PIT. Okay. So another point is sometimes there's duality in this algebraic spaces, and commutative rank and non-commutative rank match. Okay, so such spaces are well studied in mathematics. They are called compression spaces. For example, this happens when all the A1 to AM are rank 1. Okay, when A1 to AM are rank 1, commutative rank and non-commutative rank actually match. This can be proven, for example, by matroid duality theorems. So in such cases, we get a deterministic algorithm for Edmonds problem. Okay, so this was already given in Gurwitz's 2004 paper by operator scaling. So there's another interesting direction for PIT. We're studying PIT by restricting the structural properties of this matrices A1 to AM, as opposed to restricting the strength of computational models trying to compute these determinants. Okay, so this is approaching PIT from the structural side. And I should mention that there's a large body of work in mathematics to study compression spaces and this commutative rank of this symbolic matrices L. So in disguise, these mathematicians are also studying the PIT problem. They're trying to characterize when spaces are compression spaces, when proving theorems about commutative rank, duality theorems, and etc. Okay. Okay. So moving on to open problems. So our algorithm and also the algorithm of Ivanov, Shah, and Subramaniam for computing the non-commutative rank are both white box. Okay. So I'll explain what that means. So a very natural question is, can we? Okay, sorry, I didn't define this problem singular. So can we design black box algorithm for this problem of singularity, or checking if the non-commutative rank is smaller than n or not? Okay. So what do I mean? So I want you to design a set S of tuples of poly and dimension matrices such that for any symbolic matrix L, which is full rank or non-singular, there exists a tuple from this set S which witnesses the rank of L. Okay, such that the determinant of summation bi tensor ai is non-zero. So design a set of tuples of matrices which witnesses the non-singularity of all symbolic matrices which are non-singular. Okay. So this captures as a special case parallel algorithms for perfect matching in bipartite graphs. Basically, you encode the edges of the bipartite graph by elementary matrices Eij. Okay. And so since we have parallel algorithms for perfect matching now, this seems like a natural next step. And this question also arises in geometric complexity theory. So Moonal has this paper where he wants to design efficient algorithms for problems in algebraic geometry, and such a problem is mentioned as an open problem there as well, about and this NNL problem, so-called NNL problem. Okay, so this is the first open problem. Any questions about this?
Just make sure you're using the fact that NC rank is never bound on rank, right? If I find such BIs, obviously the rank is not full, right? It's not full rank in a commutative sense.
Sorry, I only meant a non-commutative rank in this case. So I want you to witness non-commutative rank.
Oh, okay. So the xi's good. So the xi's are non-commutative variables.
Yes, xi's are non-commutative variables. Sorry, yeah.
I see. Okay, sorry. I was
yeah.
mixing.
I want to design black box algorithms for computing non-commutative rank. Okay.
But then you still have to try all possible b's from the set, right?
Yeah, size of set should be polynomial.
But there's still lots of combinations of which bi goes from. Oh, S is tuples. Okay, sorry. Okay, go on.
Yeah, sorry. Yeah, S is ordered. Yes.
Thank you.
Tuples are. Yeah. Okay. Okay. So the next open problem is about checking complete checking. Okay, I didn't define this. Okay. So what our algorithm is doing is checking if a completely positive operator is rank decreasing. Okay. So what does that mean? There exists a PSD X such that T decreases the rank of X. Rank of T of X is smaller than rank of X. So it's not hard to see that this property is exactly the same as checking shrunk subspaces. Okay. And the question now is, can we check this rank decreasing properties for general positive operators, not just completely positive operators? So note that operator T from n by n matrices to n by n matrices is called positive if T maps PSD matrices to PSD matrices. And I want you to check whether positive operators rank decreasing or compute the capacity of these such operators. And in fact, the scaling algorithm works even in this case. Okay, it converges. And what is required you to prove is only that capacity of T is at least 2 to the minus poly n. Okay, so prove that when entry bit sizes of T are small, then capacity of T is at least T to the minus poly n. This would prove that you can compute capacity, the same scaling algorithm works, and you can check whether the capacity is greater than 0 or not, and so on. Okay. So somehow in this setting, the connection to non-commutative rank and this invariant theory is missing. So it's hard to get this lower bound on the capacity. Okay. So another open problems connected to Edmonds problem, I already mentioned, design a 1 plus epsilon factor approximation in deterministic polynomial time. And again, can we design efficient algorithms for the Edmonds problem assuming some structural properties of A1 to AM? So already said that when A1 to AM are compression spaces, this algorithm gives you a way of computing commutative rank as well. Okay. So the two very interesting examples which are like of matrices which are not compression spaces, but still we can do we can solve Edmonds problem in deterministic polynomial time. So one is perfect matching in general graphs. Okay, so if you look at the Tut matrix of a general graph G, right, the commutative rank of L is exactly twice the maximum matching size in G. Okay, and since we have deterministic efficient algorithms for G, we can compute the commutative rank of this Tut matrix. Okay, so this was already solved by Edmonds in '65. So another very interesting example is testing isomorphism of modules. So this is really a fancy name for this simple problem. So given tuples of n by n matrices A1 to AM and B1 to BM, does there exist an invertible matrix X such that XAI equals BIX for all I? Okay, so they're just saying that if you can change the basis in some way and convert AI to BI simultaneously. Okay, so does there exist an invertible X such that XAI equals BIX for all I? And in fact, Christoph, Ivanios, and Karpinski gave deterministic polynomial time algorithms for this problem. So you might wonder, why is this a special case of Edmonds problem? So notice that the set of all solutions X to this equations is given by a subspace of matrices. So you can construct a basis, and that will give you a symbolic matrix L, for which you want to compute the commutative rank or check whether commutative rank is full or not. So this is another instance in which we know deterministic polynomial time algorithms and doesn't seem to be a compression space. Okay, so find more interesting examples based on structural properties of A1 to AM where we can solve Edmonds problem. Okay, I'll end there. Thank you.
Ankit?
Yes.
Any more questions? So what people think about questions. Can you say a few more words about the Braskamp Lib? I know it's probably a topic for a separate talk, but if you can say a few words.
So, okay, so Braskamp Lib, so there's a set of inequalities in analysis that generalize sort of all the known inequalities that we use in TCS, like Holder's inequality or Loomis-Whitney inequality and so on. So these are given by, usually these are given by a set of matrices B1 to Bm and some numbers P1 to Pm. And I don't know. So these are of the, so what it turns out is that the optimal constants in these Braskamp Lib inequalities are given by some expression that looks exactly like capacity. Okay, and it turns out that it's really a special case of operator scaling. So that constant in Braskamp Lib inequalities can be reduced to this notion of capacity in operator scaling, and since we get a polynomial time algorithm for computing capacity, we also get a polynomial time for algorithm for computing this optimal constants in these inequalities.
It's because Gaussians achieve tightness in the inequality, right?
Yes, yes. So Gaussians achieve the tightness in inequality, and when you plug in Gaussians, you get some expression, and that expression exactly looks like capacity.
So maybe the better way to say it is capacity is the constant the Braskamp Lib, right? I think it's exactly. A much longer history than capacity.
Yes, exactly. So a special case of capacity is exactly the constant in Braskamp Lib.
Any other questions? Okay, so if not, let me just mention again that Eric Blaise will give the talk in 2 weeks on multi-user testing. And thanks again, everyone. Thanks you, Ankit. Thank you, Ankit.
Yeah, thank you.
And you're welcome to stay here. We'll just go offline. You can stay here and chat on the board offline. So.